Okay, I have another hint for you on the extra credits. So I gave you those points, but I could also tell you that this part of it here, from here to here like this, that's a parabola. Okay? That is a vertical line. That right there is circular. Of course, everything's symmetric on the other side. One line with no commas can do it. One line with no. So the reason this extra credit is somewhat a challenge. Okay, it's a challenge. But that information is also helpful besides the points I gave you last time. Okay. So let's look at this. So we were talking about springs last time. So without looking at your notes, don't look at your notes from last time. See if you could answer this question. Without your notes. What's the work required to stretch a spring with stiffness K from its natural length to X meters past its natural length? And recall that the force required to stretch a spring is K times X, the stiffness times that amount of displacement. Okay? So then how could you write a function that would give you the work accomplished for stretching it X meters past its natural length? So should be able to write that down even without looking at your notes from last time. What would that be? Think about that. Okay, Jennifer back there. Can you tell me? Do you know what it is? She said integral from 0 to x. What's that? So we want the rate of change of what quantity? If we're doing a work function, we want the rate of change of work, right? The rate of change of work. And what did we talk about last time? What's the rate of change of work? The force, right? The force. So what should I write? K X T dt. Anyone have it before I wrote it? Some. Okay? Yeah, because work is what? Work is force times distance. Right? So we see that right there is a little bit of work, right? Force times a little bit of distance that you're stretching. So that's a little bit of work, and so that's the rate of change of work. And we know that to write an accumulation function, it's going to be the integral of our rate function times dx, or we need to use t's though. So f of t wouldn't right there? Yeah, if you would have, okay, so yeah, f of t right there would also work, would also be correct, because that's what that is. Kt is f of t, yeah. So 0 to x, f of t dt, or kt, so we know that f of t is that. Okay, so that's just a review. So question, example. It takes 50 joules of work to stretch a spring from 0.08 meters past its natural length. How much additional work would it take to stretch it from 0.08 to 0.13? So I want you to talk strategy with the person next to you. Strategy. Who thinks they've got a good start to this? Volunteer. Anyone think they know how to get started? Yeah. Okay, and how are we going to find the spring constant? Careful. What is 50?
Oh, my bad.
Yes, right. It's not force. This is the amount of work, right? So this is Newton meters. It's Newton meters. But yeah, we want to find that spring constant first. How are we going to do that? Keep going or? Okay.
Could you instead of just dividing it by the distance, could you divide it by distance squared?
It sounds like you're jumping to a calculation when we want to just kind of maybe represent it first before we do that. So we just want to, if it takes 50 joules of work and we're trying to find the spring constant, what can we write? Charlotte. Not quite, because it's changing. So as we're stretching it, that force is changing always. So it's not, yeah, Katie. So 0 to 0.8 of what? What do you want? Sorry, hold on a second. So, okay, 0 to 0 0.8 of K times T dt. Is this a correct statement? Okay, so there's no dividing to solve for something here, right? Because we have 50 equals the accumulation from 0 to 0 0.8 at the rate kt dt. Does everyone see that? That to find that spring constant, we were given an amount of work, which would be like a value of the dependent variable of a function of a spring function, spring work function. Okay, and so what is problematic about this? Open form. Remember talking about open form? Open form is a form, some type of mathematical expression that's reflecting process, right? This reflects the whole first week of the course that we did. You know how fast the quantity is changing at every moment. You want to know how much of it you have at any moment, accumulation. And this is symbolizing that. This is showing how it is that we're coming up with how much you have at every moment, given how fast it's changing at every moment, the rate. So that's the advantage of open form. It's reflecting this really important underlying process. But the disadvantage is when it comes to answering a question like this. And what's the disadvantage with open form? What the heck is K? How are we going to get K, right? There's no like algebra, divide by this and square both sides to get K by itself because it's locked in this open form. So I kind of gave you a preview a couple days ago. We want to get a closed form. And what is a closed form? It's using elementary functions, basic general functions that will express this same, in this case, value, right? Or a function, right? So if we have a work function, can we get this work function in a closed form, meaning use polynomials, sine, exponential, because that we can solve and we can crank out answers really easily. But with open form, we need technology to do it, right? We need to put this in GC and let it do something for this. But even so, solving for K is a big problem. Even GC, we can't put that in. GC won't tell us what K is. So the next part of the next couple weeks of the course is we're going to be looking at, given an open form of an accumulation function, we want an equivalent closed form, a function that gives us the exact same outputs for the same inputs, the exact same function, but can do it with familiar functions, right? With familiar functions, sine, cosine, polynomials. linear functions, exponential functions, log functions, etc. In other words, closed forms. Okay, so just before we start that, one more example of this we saw a couple days ago. Remember we had the ant was pushing the seed, and the ant was pushing along this was the curve the ant was pushing along. Is that open form or closed form? Closed. Watch how fast GC can graph that. Did you even see it? Did you even see the points being generated? Here, I'll do it again. Watch. So I'm going to hit the graph button. It's like instantaneous, right? Why? Because it's graphing a closed form. A closed form, which is the values are computed really fast, especially if you have technology. Okay? But what about the work? Now we saw this force function was dependent on how far the ant had pushed the seed, and so we had to get that distance that the ant had pushed, and that was our arc length function. And so then the rate of change with respect to x, the horizontal, was this force according to how far the ant had pushed, which is this open form expression, scaled from horizontal to the direction that the ant was going, right? So this is the force that the ant was pushing with at s meters, having walked s meters, and then we had to scale that so that we could have our independent variable be x, right? And so then our work function was the integral of the rate of change. So that rate of change involves a force that involves an integral. And then so the work is the integral of a rate function that involves an integral. And those are, right, expressed in open form. And we said, what happens when we try to graph that? So I'm going to graph from 0 to x for x greater than 0. So you saw how fast the open form got graphed. What about the work function? Why is it taking so long? Because it's evaluating this function as open form, and not only as open form, but the rate function is defined in open form because it's a function of this arc length function. Okay, so this is underscoring that open form is not readily computable. Even GC, it's taking it a long time to come up with this graph of this based on an open form expression, whereas that one just graphs in an instant based on closed form. So we have very high motivation to be able to write these open form accumulation functions in closed form, okay? Because they do quick work for us, whereas the open form doesn't do quick work, but reflects that underlying process, which is also very important. Okay, so let's get started with this. So how are we going to write these? So we have the tools. We just got to review the tools to write these open form accumulation functions in closed form. So we start with, what's the net accumulation of a quantity given by function f starting from x equals a? So a quantity function is given by f, and we want the net accumulation. We want to write it in such a way that it represents the net accumulation. What would that be? I'm doing it all semester. Jerry, what would it be? Integral? The integral of f? So the quantity is given by function f. So it would be the integral of the the rate of change of f, right? So this is our net accumulation function for a quantity given by f, right? The net accumulation starting from a, right? Net accumulation quantity given by f starting from a. We need the rate of change of f. So how can we write the function f, the total accumulation of the quantity, in terms of this integral? So now we want to write total accumulation of f at x. What would the total accumulation of f at x be? She said f of a plus that. What do you think? Yep, so it's all the accumulation up to a, according to f, plus now the net accumulation starting from a, right? Okay, so if we subtract f of a from both sides, we get this. F of x minus f of a equals the net accumulation from a to x. So both of them are expressing net accumulation, but in different ways. The left side, how is it expressing net accumulation? As? Okay, so it could be closed form. That's right. That's where we're going with this. But what does f of x minus f of a represent? How does it represent the accumulation from a to x? Final minus initial, right? The final amount of the quantity minus the initial amount of the quantity. Final minus initial. And this other side we know is the accumulation of many small bits, right? Starting from a, accumulate bit by bit. But both then give the accumulation the exact amount of change from a to x. Okay, so we've got this equation right here, and this is the fundamental theorem of calculus. Okay, that the accumulation of many bits using the rate function is equal to the net change that you get, or the final value of the quantity minus the initial. And so we're going to use the fundamental theorem. This is our key. The fundamental theorem is our key to writing these accumulation functions, open form, in closed form. All right, so closed form is going to look like this. Closed form for our accumulation functions is going to look like this, where we're going to have to figure out what f is. Is it a sinusoidal function? Is it a polynomial? Is it a combination of those? So the question is, how are we going to figure out what f is? So what is f? So if we have the open form, then where are we going to get this function f that we're going to evaluate? We're going to write it as f of x minus f of a. Where's that function f going to come from? Okay, so what is it compared to the rate of change? If we have the rate of change of f, then what is f? Let's say it the other way around. If you had f, how would you get the rate of change of f? Derivative, right? So if you have the rate of change of f, how will we get f? Antiderivative. Antiderivative is going to be our key to finding closed form accumulation functions. F is the antiderivative of the rate of change of f. Okay, so this is the key here. So the key is fundamental theorem of calculus and knowing antiderivatives. Then we can write these open form accumulation functions in closed form. So we can just get started. Here we go. So I'm going to give you some expressions. For each one, I want you to explain the full meaning of the expression, include all the specifics. Okay? So start with that. And then I want you to use the fundamental theorem to write a closed form, knowing that this function f is going to be the antiderivative, or the function whose derivative is the rate that you're given, right? You're thinking about what function, if I took the derivative of it, I would get this rate function that I have in the open form. Okay, and then if it's appropriate, you can solve or simplify that closed form. So in part B, I'm saying computable expression. I'm basically saying find the closed form. So we're going to start with easy ones, and then in the next couple weeks, we're going to look at techniques to do harder ones, right? Harder ones. But today we'll just get the idea and do some easy ones. So again, what are you going to do with this? You're going to, first of all, explain the meaning of that. And that's just practice of what we've been doing all semester. What is the meaning of that? If you saw that, What would it mean? And include all the specifics. And then try to write it in closed form based on the fundamental theorem and what we talked about. And then if that can be simplified, simplify that as much as you can. All right? And so I got 4 of them for you while I take some attendance. But don't skip over part A. So make sure you got part A and you include all the specifics. Again, what you're thinking about is looking for this function f, and I'm asking what function, if I took the derivative of it, would be the rate function, right? That's what an antiderivative is. What function, if I were to take the derivative, would I get that? That's your function f. And then your closed form will be that function evaluated at x minus that function evaluated at a. All right, so take your time, talk it out, and I'm going to take some attendance. Alex, tell me about the meaning of this. How would you describe what that is or means? What? No, negative 1/2. He said the accumulation from negative 1/2 to x at a rate of is it the rate cosine u du? What's the rate? Okay, at the rate of cosine of x. What do you think? Yeah, this is a net accumulation function, right? If you see that, you think, oh, this is a net accumulation function. What are the details of this net accumulation function? How is my quantity accumulating? How is it accumulating? At a rate of cosine x. I have a quantity that's accumulating at a rate of cosine x, and this function is going to tell me what? The net accumulation of that quantity having started from negative 1/2, right? If it's accumulating at the rate cosine x, right? It's the net accumulation starting from negative 1/2. Okay. All right, so what about a closed form? How am I going to get the closed form? Edmund, what do you think? Remember what we said? So the closed form is going to look like this. We just need that function f. Right, exactly. What function has the derivative cosine x? Remember? So what function, if you took the derivative of it, you get cosine x. Sine, right? So now our function f is sine, so we can write the closed form, which would be final minus initial. Sine of x minus sine of negative 1/2. Now tell me about that function. How would you describe what that function is? Okay, but what is the function? What is that function? What is it? What does it do? Net change of? It's the net accumulation function of a quantity whose rate is cosine x starting from? It's the exact same function. It's the exact same function that you described in part A. What's the difference now? Closed form. This is computable now. We can give it values of input, values of x, and we can just crank out the corresponding accumulation or net accumulation. Whereas this, we'd need technology to do it. Right? So it's the exact, for the same independent values, it gives the exact same dependent values, which is the net accumulation starting from negative 1/2 of a quantity whose rate is cosine x. Okay, so now you've got the pattern, so work on these other three. Is it the net accumulation of the rate? The quantity that has that rate, right? It's a net accumulation of some quantity that has that rate. Okay? And did you get a closed form for that? Because the antiderivative of 3e to the x is? Right, so if you take the derivative of 3e to the x, you get 3e to the x, right? That's that special function whose derivative is the same, the rate of change is the same as the amount. So our f is 3e to the x. And so we're going to do 3e to the x minus, which is just 3, right? So 3e to the x minus 3. So Mark, what's the meaning of that function? 3e to the x minus 3. What's the meaning of that function? Good, right. So it's the net accumulation. It's the same as this. It's the net accumulation of a quantity whose rate is 3e to the x, starting from 0, right? Starting from 0. And that it's just enclosed. The only difference is this enclosed form can generate rapid results for us. Okay, next one. Kevin, what's the meaning of that third expression? Nailed it. Did you hear him? Absolutely nailed it. Did you get, so now we've got x to the fourth, and we need to build a closed form from that. So what function has a derivative x to the fourth? Did you come up with it? X to the fifth. So x to the fifth, right? So we're thinking about what function gives us a power of 4 if we take the derivative? Well, instead of lowering the power, you'd have to raise the power, right? But does x to the fifth do it? No, because, so here's the idea that we could try x to the fifth, and if we take its derivative, what do we get? 5x to the fourth. And there's a 5 there that we don't have here. So then our second attempt would be 1/5 x to the fifth. So we're going to do 1/5 x to the fifth. And keep going. One-fifth 1 to the fifth. Final minus, so now it's this net accumulation function is expressed as final value of the quantity minus initial value of the quantity, right? So that's 1/5 x to the fifth minus 1/5. Questions on that? Okay, so next one's harder. So we've got this function 2a times the square root of a squared plus 3, and we're trying to think of what function has that as its derivative, right? What function has that as its derivative? Maybe we should figure out which derivative rule was used to get that first. So what derivative rule would end up looking something like that? You should remember the chain rule, right? The chain rule where you have the kind of the derivative of the whole thing and then times the derivative of the inside part. So which was the derivative of the inside part? Do you see that if this is like the result of a chain rule derivative, that 2a is what we got when we took the derivative of the inside. Do you see that? So then what was the original function then? So when we took the derivative, this 2a popped out, so it wasn't there to start with. So we're really looking at this and asking what's the antiderivative of that? A squared plus 3 to the 3/2. You see that? Because this is also the 1/2. Remember, when you take the derivative, you reduce the exponent by 1. So antiderivative means add 1. Now is that, sorry, it should be x. Does the derivative of this now equal exactly what the rate function we started with? Because if we took the derivative of this, we'd have 3/2 times this to the 1/2 times 2x. So how do we adjust it? You see that a 2/3 is going to make its derivative be exactly what we started with. So that's harder, but that's what we're going to start practicing. What I just talked through. We'll give you kind of a little more structure to it. We're going to practice that. But here's the point. It's like we're trying to figure out what function has a derivative of the thing we're given. So what can you do? You make an attempt, and then what do you do? So if I'm not sure, right? Just make a stab at it, and if I'm not sure, what can I do? Take the derivative. That is the huge point. That the whole point is we're trying to come up with something that has a derivative of this. So you can make a guess, and it can be a little bit wrong. That's okay. Take the derivative and check it. Okay? So if we were to take the derivative, what would we have? 3/2 times 2/3 goes away. X squared plus 3 to the 1/2 is square root times derivative of the inside 2x. That's exactly what we have. Okay? But then we're not done with our closed form, right? Minus 2/3 103 to the 3/2, right? 10 squared plus 3. So there's our closed form that gives it's the exact same function as this net accumulation function, starting from 10 for a quantity whose rate is 2x times the square root of x squared plus 3. This function is exactly the same as that one. But it's in a computable form, closed form. Okay, so if you're a little sketchy on what I just did there, that's okay. This is the type that we're going to now work on. This is what we're going to be calling undoing the chain rule. All right, because this antiderivative we undid what the chain rule did to get that derivative. So we're going to call this undoing the chain rule. So if we're really going to be good at undoing the chain rule, we have to be really good and understand the chain rule. So we're going to just practice some chain rule derivatives here. So here are 4 functions. Maybe let's put this one last. Okay. So this first one, I gave you a little hint there to write it as something to a power first, and then take the derivative. The other ones, more straightforward. So this is you're remembering your mastery test, right? This is stuff you did in the mastery test. Okay. So those of you who have been waiting for algebra in this course, here's your chance. All right. Mastery test, algebraic rules. To the negative 1/2. So that's how you would rewrite that first one. Okay, so derivative is, so all right, volunteer. Let's see. Yeah. Yep. Make sure you put parentheses around the second part, or else you'll only multiply the first one times the first part. Minus what? And then that is a constant, right? Derivative is 0. How about the next one? Somebody else? Yeah? Okay. Did you get it right? Next one. Yeah. Okay. Finally. Michelle, did you get the next one? Yeah. Uh-huh. To the Okay, so notice the pattern in all of these, right? You do the derivative of the outside function, right? Leaving the inside as it is, and then you multiply by derivative of the inside. So now, if you're given one of these on the right, and you have to recover antiderivative, recover the original function, what are you going to focus on to recover the original function? Exhibit A or Exhibit B? Which one of these are you going to focus on to recover the original function? So let's look at the last one. Does looking at the 4x cubed allow you to recover this? Does looking at this allow you to recover that? Yes. This has all the information you need to recover that function. Do you see that? So this is what we're going to do. When we get functions, rate functions that look like this, that we see, oh, that's the result of the chain rule. We got to find the part of it that's Exhibit A. Because the part of it that's Exhibit A is the one that's going to be the key to recovering the original function. Does it make sense? Okay.